Representation Theory of Finite Groups, Lecture 24, the Determinantal Formula. Let us recall what we did on the previous lecture. Let n be a positive integer. For a partition lambda of n, consider the set SYT lambda of all standard Young tableaus of shape lambda. For a box V in lambda, let H lambda of V denote the length of the hook for the box V in lambda. The hook for V consists of all boxes to the right of V in lambda and all boxes below V in lambda. Here is an example. If lambda is a partition 6, 4, 4, 3, 1, and we take as the box V this box which is in the third column and in the second row, then its hook consists of all boxes to the right of V and all boxes below V. So these boxes are marked by bullets. So the length of the hook for V in this case is 4. During the previous lecture, we saw the following hook formula, that for any partition lambda of n, the cardinality of the set of standard Young tableaus of shape lambda equals n factorial divided by the product over all boxes V in lambda, and the factor corresponding to this box V is exactly the length of the hooks for V in lambda. Today, we will give another formula to compute the same cardinality. So we recall the usual convention that 0 factorial is equal to 1, and we will use the conventions that 1 divided by r factorial is equal to 0, provided that r is a negative integer. Theorem, usually called the determinantal formula, for a partition lambda of n of the form lambda 1, lambda 2, and so on lambda k, the cardinality of the set of standard Young tableaus of shape lambda is equal to n factorial times the determinant of the k times k matrix, for which in row I and column j we have the entry 1 divided by lambda I minus I plus j factorial. For example, if lambda is the partition 2, 2, 1 of 5, then the corresponding determinantal formula looks as follows. The cardinality of the set of standard Young tableaus of shape 2 to 1 is equal to 5 factorial times the determinant of the matrix in which the first row is 1 divided by 2 factorial, 1 divided by 3 factorial, 1 divided by 4 factorial. The second row is 1 divided by 1 factorial, 1 divided by 2 factorial, 1 divided by 3 factorial. And the third row is 0, then 1 divided by 0 factorial, 1 divided by 1 factorial. So we know that 1 divided by lambda 1 factorial is the first diagonal element, 1 divided by lambda 2 factorial is the second diagonal element, and so on. And then the numbers in the denominator increase by 1 from left to right in each row. And if this number is negative, then the corresponding 1 divided by r factorial is 0. Here is how we will prove the determinantal formula. We will use the hook formula, which we already proved. And if we compare the determinantal formula and the hook formula, then we see that in order to prove our determinantal formula, we only need to show that the determinant in the formula equals the 1 divided by the denominator of the hook formula. We will use the following notation. For a box V in j's column and in i's row, we denote by hij the hook lengths of the hook for V. Note that for any I, hi1 plus I is equal to lambda I plus k. So lambda I plus k is exactly the number of boxes in the i's row of lambda, this is lambda I, and in the first column of lambda, this is k. So note that the box in the first column and in the i's row, it is counted twice here. And here we have the hook for that box plus the height of that row. Also note that in the determinantal formula, each row in our determinant has the following form. So we have reading from right to left, 1 divided by some h factorial, then 1 divided by h minus 1 factorial, 1 divided by h minus 2 factorial, and so on. And here h is some non-negative integer. And in the proof below, we will use elementary row and column operations to reduce the determinant to a simpler form, and then we will use certain type of induction. So let us prove our formula. So we need to understand our determinant as appears in the determinantal formula, and we use our observations that lambda I plus k is equal to hi, 1 plus I to rewrite this determinant in the form as follows. So in row I and column j, we now have the entry 1 divided by hi1 minus k plus j factorial. So lambda I minus I is equal to hi1 minus k. Consider now row I. So row I in this notation, reading from right to left, has the first element 1 divided by hi1 factorial, then 1 divided by hi1 minus 1 factorial, then 1 divided by hi1 minus 2 factorial, and so on. So what we do, we take out 1 divided hi1 factorial from row I. We do such a manipulation for every row, but we follow what happens to an arbitrary row, let's say row I. What is left in row I now looks as follows, reading from right to left. 1, then hi, 1, then hi, 1 times hi, 1 minus 1, and so on. So starting from this row, we subtract the last column from the penultimate column. So this operation doesn't change the determinant. So we multiply the last column of our determinant with minus 1 and add it to the penultimate column. And the outcome looks as follows. So the only change here is this minus 1. So if you multiply 1 with minus 1 and add here, we get hi minus 1 minus 1. The rest remains the same. The next operation is that we multiply the penultimate column with minus 2 and add to the third column from the right. So the outcome will be as follows. So the only changes here. So if we take minus 2 times hi, 1 minus 1, and add to hi, 1 times hi, 1 minus 1, we will get hi, 1 minus 2 times hi, 1 minus 1, and the rest is the same as before. And we proceed in a similar way. So next step, we multiply the third column from the right by minus 3 and add it to the fourth column from the right. And the outcome looks as follows. The only change is here. So we have this expression which we multiplied with minus 3 and added. So we will get here minus 3. And this is a new form. And this operation again does not change the determinant. And we do it all the way until we change the leftmost column of our determinant. So the leftmost element in row I after this last change will look as follows. So this leftmost element before that operation was a product of hi, 1 times hi, 1 minus 1 and so on. And now we took this product, multiplied with minus times k minus 1 and added. So instead of hi, 1, we will get the factor hi, 1 minus k plus 1. Our next action is we move back almost all what we moved out. So we moved out 1 divided by hi, 1 factorial. Now we move back into row I 1 divided by hi, 1 minus 1 factorial. And when we do that, In row I, we will have, reading from right to left, 1 divided by hi, 1 minus 1 factorial, 1 divided by hi, 1 minus 2 factorial, and so on. Since we moved in almost everything what we moved out, so for each row we kept one factor outside the determinant, we also have the remaining factor outside the determinant, which is 1 divided by the product over all I from 1 to k, hi, 1. So now, if we consider the partition mu, which is obtained from lambda by subtracting 1 from each part, then the determinant which we now obtained is basically the same determinant as for the partition mu in the determinantal formula. What this means will be explained on the next slide, but then the determinantal formula now follows by induction, because we moved out the product of all hooks for all boxes in the first column, and then we subtracted the first column. So what exactly do we mean by basically the determinant for mu? If all parts of lambda are greater than 1, then the new determinant which we get is exactly the determinant for mu as given by the determinantal formula. In case the last part of lambda is equal to 1, and maybe some other parts of lambda are equal to 1, then the matrix for the new determinant will be size-wise bigger than the corresponding matrix for the determinant for mu. So if we denote by m the maximal part of lambda which is greater than 1, then the new determinant which we get will have the following form. It will be block upper triangular with the first diagonal block of size m times m, and this will be exactly the determinant for mu as given by the determinantal formula. Then we will have the second diagonal block, which is a matrix of size k minus m times k minus m, and this matrix will be upper triangular with ones on the diagonal. In particular, the determinant of this bigger matrix will be equal to the determinant of the first diagonal block, which justifies our induction step in the proof of the determinantal formula. Here is an example. So let us now see how the proof works, and in particular how the induction step works for the partition 2, 2, 1. So this is the original determinant. We have already seen it as an example. So we move 1 divided by 4 factorial from the first row, 1 divided by 3 factorial from the second row, and 1 divided by 1 factorial from the third row. So this is the outcome. In the first row, we have 1, 4, and 4 times 3, reading from right to left. In the second row, we have 1, 3, and 3 times 2. And in the third row, we have 1, 1, and 0. So next, we subtract the last column from the penultimate column, and the only changes we will have 3, 2, and 0, the new penultimate column. So next, we have to multiply this penultimate column with minus 2 and add to the third column from the right. So the only change will be in the third column from the right, and instead of 4 times 3, we will have 3 times 2, and instead of 3 times 2, we will have 2 times 1. So this will be the new determinant. And next, we move 3 factorial in the first row, 2 factorial in the second row, and 0 factorial in the third row. And the outcome is 1 divided by 4 times 3 times 1. So this is the product of hook lengths in the first column. And then the determinant of the matrix, where the first row is 1 divided by 1 factorial, 1 divided by 2 factorial, 1 divided by 3 factorial. The second row is 1 divided by 0 factorial, 1 divided by 1 factorial, 1 divided by 2 factorial. And the last row is 0, 0, and 1 divided by 1 factorial. And we see that this is an upper block triangular matrix in which the first diagonal 2 times 2 block is exactly the determinantal formula determinant for the partition mu, which is obtained from lambda by subtracting 1 from all parts. So it is the partition 1, 1. And of course, we can directly compute this determinant as a determinant just to check that everything is correct. So let us compute the number of standard Young tableaus of shape 2 to 1 using the determinantal formula directly. So by the determinantal formula, it's 5 factorial times our determinant, which we already seen a couple of times. So what we do, let's move 5 factorial into the first row. So if we do that, the first row will be reading from right to left 5, then 5 times 4, which is 20, and then 5 times 4 times 3, which is 60. Right, and then the second row is just 1, 1/2, and 1/6, and the last row is 0, 1, 1. So this is 3 times 3 determinant, which we compute directly. The product of the diagonal elements is 60 times 1/2. Then we have the product of these 3 elements, which is 0. And we have the product of these 3 elements, which is 5, with the sign plus. And now the negative part of the determinant, the product of the elements on the second diagonal is 0 because of the 0. And then minus 60 times 1/6 times 1. So minus 60 divided by 6, and minus 20 times 1 times 1, minus 20. So this gives us the expression 30 plus 5 minus 20 minus 10, which is equal to 5. So the determinantal formula applied to the partition 2 to 1 gives us 5. Let us also compute the number of standard Young tableaus of shape 2 to 1 using the Hooke formula, just to compare. So if we take the partition 2 to 1, then by the Hooke formula we will have 5 factorial divided by lengths of all hooks. So the hook here has length 4, the hook here has length 2, the hook here has length 3, and the hooks here and here have length 1. So we have 5 factorial divided by 4 times 2 times 3 times 1 times 1, which is equal to 5. So we have the same answer. So let us finish with some problems and questions. Question 1. Prove with all details that hi(1 plus I) is equal to lambda I plus k. Question 2. Check with all details that in the case lambda k is equal to 1, the determinant of the bigger matrix in our induction step coincides with the determinant for mu. Question 3. Write down and compute directly the determinant in the determinantal formula for lambda being the partition 3, 2, 2 of 7. Question 4. Check how the first induction step works for the partition 4, 3, 2, 1, 1. And finally, question 5. Prove another formula for the cardinality of the set of standard Young tableaus of shape lambda. Namely that this cardinality is equal to n factorial times the following fraction. The numerator is the product over all I smaller than j, hi1 minus hj1, and the denominator is the product over all I of hi1 factorial. Thank you very much, and see you next time.